At Karolinska University Hospital in Stockholm, researchers are examining the use of machine learning, often referred to as artificial intelligence or AI, to improve the efficiency of breast cancer screening. The results so far are highly encouraging. While human radiologists have a detection rate of around 77%, preliminary studies indicate that an automated program trained using machine learning has a detection rate of 82%. Currently, trials are being run where the AI is used to prioritize high-risk cases for further human analysis. But the widespread use of machine learning and AI in practice is not some distant future. Already, machine learning is everywhere. It trades on our stock markets, it recommends content on social media, and it operates autonomous vehicles. But how does it work? How do machines learn, for instance, to diagnose breast cancer? At their core, most AI algorithms are made with the following recipe. First, collect and annotate as much data about a given task as possible. Then, construct a highly complex adaptive computer program. And finally, train the program on the annotated data until it can perform its task well. In the study at the Karolinska Hospital, the dataset consists of thousands of examinations of previous patients who are confirmed to have had breast cancer or confirmed to have been healthy. However, while the algorithm can only train on the data we collected, what we actually want is for it to perform well on new data that it has not been exposed to during training. This raises the question: how do we know that the algorithm actually does perform well on new data and not just on training data? In other words, how do we know that the algorithm is able to generalize its knowledge? Finding the answer to this question is vital to increase the reliability and trust of machine learning systems, especially if we are to put our lives in the hands of automatic diagnostic systems. Since the deep learning revolution for computer vision in 2012, AI technologies have demonstrated impressive feats in tasks like object recognition, although this does not always go smoothly. For instance, an AI algorithm may be unaware that cows are basically never 5.2 meters long, and the self-driving software that Tesla uses is not entirely sure what to make of an open horse carriage. Recently, huge strides have been made in the field of AI-generated images. With tools like Stable Diffusion and DALL-E, users can input any text prompt they want, and within minutes, several artificial new images based on this prompt are generated. While input prompts like dog are expected to work well, surely the AI has trained on pictures of dogs after all, these algorithms can also produce fascinating results for absurd prompts that cannot possibly have been included in the training set. How about old lady building her nest on a cliff face? More creative prompts with mind-boggling results can be found on the Twitter account Weird DALL-E Mini Generations. So, how does this all work? How are AI algorithms able to sometimes use training data to perform well in new, unfamiliar situations, while at other times they fail? A possible explanation for this mechanism comes from the field of information theory. Information theory is a mathematical framework developed in the late 40s by Claude Shannon, who also dabbled in unicycle juggling. Information theory is the mathematical field upon which the modern digital world, with Wi-Fi, Bluetooth and 5G communication, is built. So, how does this relate to the question of whether AI algorithms generalize? The underlying idea is that the generalization ability of an AI algorithm is related to the information that it extracts from its training data. To understand this, consider two different students using a list of examples to learn multiplication. The first student just memorizes every multiplication problem from the examples, even the ones where there is a typo, but they do not think about why the answers are what they are. The second student, however, looks at the examples and understands that n times m equals m added to itself n times. When solving problems from the example set, both students will perform quite well, and the first student will even get a 100% despite the typo in the examples. But when trying new multiplication problems that did not appear in the list, the first student will struggle, as they do not recognize the problems. However, the second student will still perform well by applying their formula. The first student committed all of the information from the examples to memory and performed well on the examples they trained on, but could not transfer this to new problems. The second student compressed the information to its most useful core, without memorizing the exact numbers that they had practiced on. They captured only the relevant information and generalized to new examples. This is similar to how, if you understand the content of a text well, you can summarize the main points in a few sentences. If the text is in a language you don't know at all, your only chance to summarize it without losing the relevant information is to copy the text word for word. This same insight is captured by Einstein's quote: "If you can't explain something simply, you do not understand it well enough." In this sense, compression is comprehension. This is the fundamental insight that information theory can bring to the study of machine learning and AI. By using the mathematical tools that underpin communication networks in the modern world, it can be rigorously demonstrated that if a learner only captures the relevant parts of the data that they learn from, they can generalize this knowledge to new examples. An AI program that just memorizes the previous patients that were diagnosed with breast cancer will perform well in training. But to perform well on new patients, the program must identify the relevant part of the medical examination. While it is still unclear exactly how modern AI algorithms are able to generalize from training data to new, unseen examples, recent research indicates that this information theoretic explanation may, at least partially, hold the key to this pertinent question. Understanding why and how this sometimes works successfully and fails miserably at other times is crucial for the safe implementation of these algorithms in areas of our life where the stakes are literally life or death. Thank you for watching.